since this is a school, a lot of the material that I will cover is classic. And there are lots of references, literally tens of thousands of references. And there's no way I could do justice to it. So I decided to put only a few references on the slides. And most of the material refer you to two papers, this one and this one. I assume you can see the pointer. Can you see the pointer?
Yes, we can.
Two papers which have a lot of the material I'll be talking about, and also have a lot of references to earlier papers. So before I start, what's the goal of this talk? So a lot of people here did, and also later we talk about fractals. And from my perspective, fractals is not just fractals is particles with restricted mobility that you heard about and so forth, but it should be viewed more generally as a number of systems, an ever-growing number of systems, and they are still theoretical, and they're very puzzling in many ways that I will talk about soon. They have a very clear lattice formulation, which is completely rigorous, completely well-defined, but they do not fit the general framework of quantum field theory. So I was asked by the host, by Dan Renhan, to talk about continuum quantum field theory for fractals. But I thought I would frame it a little bit more generally and talk more generally about the topic of the relation between lattice theories and continuum quantum field theory. And I view this topic as very central, as I will soon outline in the coming slides, both from the more mathematical, more high energy view of the subject, and from the more condensed matter aspect of the subject. This interplay between lattice theories and continuum will be very significant, and I will talk about it at length. Now, the lattice systems, so the quick comment is that the lattice system is always rigorous. There's a finite number of degrees of freedom, nice Hamiltonian or nice action if we use Euclidean formulation. But the continuum quantum field theory formulation is less rigorous. So I was allowed to use this quote by our host that the continuum is so slippery. I'm not quite sure what he meant by that, but I'm sure this was not. But I'm sure this wasn't a positive comment. And this will be kind of a theme of this talk. I will go back and forth between the lattice and the continuum. And whenever you will feel a little bit uncomfortable, or you will feel that the continuum theory is slippery, I'll immediately jump back to the lattice to make sure we know what we are doing. So what I will do is start not with any one of these exotic systems, but I'll start by reviewing a well-known system from a perspective which is slightly new, but I think it gives a nice overview of the standard systems in a way that will allow us to jump in the later part of the talk to the more exotic ones. So I'll start with known systems, specifically the XY model in 1+1 dimensions, and then I'll jump to the exotic systems. And the exotic systems I will talk about do not yet quite have fractons, but they have many of the subtleties of fractons, and in particular, subsystem global symmetry, and I will define that soon, and the associated subtleties. So here the system will be a global symmetry, and the next step will be to gauge these symmetries. So this is kind of a general overview. I'd like to start with an introduction of lattice versus the continuum theory. So continuum field theory is enormously successful. It has dominated physics for almost a century now. It has a lot of success in different branches of physics, yet it's not mathematically rigorous. So the people who are more mathematically inclined, this is a huge challenge. It's clear that there's something very deep going on, but its mathematical foundation is not yet solid. My personal belief is that this is not just a problem for the mathematicians. This is something that physics will also benefit from making this connection more, making the system more rigorous. So given a continuum system, one way to regularize it is put it on the lattice. An example to keep in mind, you want to define an integral, you write it as a sum, and this is the Riemann sum, then the sum, assuming the sum converges, it's very nice. And then the challenge is to prove that the continuum answer, the result of the integral, is independent of how we break the sum, independent of how we regularize it. In another context, in geometry or in topology, we have a complicated manifold with complicated topology and maybe subtle metric, and we triangulate it. And then we would like to argue that the result of the continuum system is independent of the details of how we regularize it. It's independent of the details of the triangulation. So this is something which is well known. And in the two examples I just mentioned, this has been beaten to death for centuries. And in the context of quantum field theory, it's not yet rigorous. And that's why we have a challenge. So we regularize the system on the, put it on the lattice, either Hamiltonian formulation or Euclidean space-time lattice. And throughout these talks, I will jump back and forth between these two formulations. And the advantage is that then the system is well defined. In the Hamiltonian formulation, we have a finite number of degrees of freedom. In quantum mechanics, there's a nice Hilbert space, everything is well defined. And in the Euclidean path integral, the path integral is an ordinary integral or an ordinary sum, finite dimensional integral, and then we just have to check that the integral converges. The next step is to take the continuum limit. So we introduce a lattice spacing, and we want to take the lattice spacing to 0, the number of sites to infinity, and the way we do that is by holding all the physical lengths fixed. So the number of sites goes to infinity, the distance between the points goes to 0, but we keep the length fixed. That's what we do when we try to perform turn the Riemann sum into an integral, or when we consider a triangulation of a manifold. And the objects of interest are correlation functions of operators whose separation is much larger than the lattice spacing A. And we'll see a lot of examples of that. So in this line of thought, the lattice gives us a definition of the continuum field theory. So we would like to define the continuum field theory, and we define it by studying it on the lattice. It is its UV, or short distance version. There's a totally different perspective, which is in a way opposite to that, which is common in condensed matter physics. Here, the problem is defined on the lattice. We start from a well-defined lattice. We have atoms, and they interact with each other, and they have spin interactions or electromagnetic interaction, and it could be quite complicated. And here the goal is to find the low energy for long distance limit. We will define the system, or the problem is defined at short distances on the lattice, and the answer is what the system does at long distances. Notice that this is the opposite of what we had on the previous slide. Here, the problem is defined at short distances, and we would like to find out what happens at long distances. On the previous slide, the continuum field theory was defined at long distances, and we wanted to find the regularization of it at short distances. And here, this is extremely powerful and extremely useful, because it's expected that the low energy behavior, the long distance behavior, is described by an effective quantum field theory. At long distances, the separation between the sites of the lattice are not important. We have lots of sites. We have a macroscopic number of sites, and we can think that everything is nice and smooth, and we describe everything by a continuum field theory. Another advantage of it is that on the lattice, we can have all sorts of interactions, very many interactions. In fact, we can write an infinite number of interactions. But it so happens, and it comes under the name of universality, that only a finite number of the parameters are important for the continuum description. So it's only a finite number of parameters to control the long distance behavior. In that sense, the description is effective. It's effective because we replace a problem that is summarized by, which is stated in terms of an infinite number of parameters, and we formulate it in terms of a finite number of parameters. In that sense, it is useful. Often, the new system, after we go to long distances, this effective system, has new properties which are not present at short distances. There could be new symmetries which are not present in the regularized system, or there could be various new dualities, and we'll see examples of that. This has been enormously powerful, this view of a lattice system at short distances, and the continuum quantum field theory description of it at long distances has been enormously powerful over the last several decades. I think it's almost a century now. And it describes the phases of matter and the phase transitions between them, and a lot of properties, including technological advances, follow this approach. So unlike the previous perspective, where the lattice was a device used in order to define the continuum theory. Here the situation is the opposite. The problem is formulated at short distances, and the answer is at long distances. However, these two approaches are not without challenges. I'll just enumerate them quickly here. Thinking that the lattice is the solution of defining a quantum field theory, this is perhaps the most powerful way to define quantum field theory. The lattice is perhaps the most powerful way to do that, but it doesn't always work. First of all, we need to prove that the limit exists, and it's independent of what happens at short distances, independent of the details of the lattice. This is something I've already mentioned, that this is analogous to defining an integral or triangulation of a manifold. So this is something that needs to be proven. But even if we know how to do that, there are many continuum quantum field theories that cannot be written on the lattice. Their behavior depends on the topology of field space, which depends on the continuity of the field. So we'll see examples of that soon. There are some terms that we can write in the Lagrangian or in the Hamiltonian that cannot be written on the lattice. Various things that are associated with the topology of field space. So the issue is various topological terms in the action, various certain global symmetries, and I'll give examples, and the topic of anomalies, and I will also talk about that. The problem is actually much worse because some continuum quantum field theories do not admit a suitable Euclidean action. So we know that there is no way to write the system on the lattice. It violates certain principles. And even more so, some quantum field theories do not even have a continuum Lagrangian, let alone a lattice version of it. So I'm not going to say anything about that, but this is just to tell you at the beginning that the lattice, as far as using the lattice as a way of defining the continuum field theory, even if we do that, and even if we prove that it's independent of the details of the lattice theory, which would be an enormous advance, even if this thing happens, it does not solve all the problems. In the opposite directions, we can ask, can we always find a continuum field theory for a given lattice model? And this is what I will really be talking about in these talks. There are some exotic systems. The one I will focus on today is the XY plaquette model that was first introduced by Paramakanti, Dallens, Fisher, and a lot of follow-up work, and I'll discuss it in detail. There are also fracton models. I gave some early references here, and there's a lot of follow-up. I'll also discuss some of that later. And these systems do not have a standard continuum field. Even before we get into the details, it's easy to see that no standard continuum quantum field theory can capture it. So just as I said before, not every continuum system can be placed on the lattice. Here we see that not every lattice model leads to a continuum field theory at long distances. So this is the challenge I would like to talk through in these two talks. But in order to do that, we should first start from a system that we do understand. A system that we understand the lattice, we understand the continuum, and we fully understand the relation between them. And I would like to review it here. And I do not know the background of the audience, so that might be too elementary, but I can assure you that I will make some comments that are not widely known, and some of them are actually quite new. But this discussion will allow us to calibrate our understanding and make sure we know what we're doing. And it will also be phrased in a way that will make it easier to tackle the more subtle systems. So let me start right now and ask if there are any questions.
Any question? Okay, now I do have one, more like a reference. So when you take a continuous limit, and not many times you have to regularize, when you have a symmetry, I assume the regularization also have to respect the symmetry. Is that a well understood phenomena, or?
This is a fantastic question. So everybody quotes me as saying that we are confused in the system in quantum field theory in general, go after the symmetry. Because the symmetry is something that is relatively easy to define, and you can check whether the system has a symmetry or not, regardless of all the other details. And that would be indeed one of the focuses, or one of the foci of these talks, understanding the symmetries, and in particular ordinary symmetries, subsystem symmetries, gauge symmetries, etc. I hope it answered your question.
Yeah. Question before continue? I think no questions, so please continue.
Okay, so let me start with the example. So it would be the canonical example. It's one of the most studied quantum field theories, arguably the most studied quantum field theory. And my terminology would be that the number of dimensions is 1 plus 1, because in high energy physicists and condensed matter physicists use different ways of counting dimensions. So by writing it as 1 plus 1, this is what condensed matter physicists call 1 dimension and high energy physicists call 2 dimensions. But this way of writing it, there's no ambiguity. So we're going to use a Euclidean lattice. Normally it's discussed in a Hamiltonian formulation, but as I promised you, I will move back and forth between Hamiltonian and Lagrangian, depending on which one is more convenient. So we're going to start with a lattice, a 1 plus 1 dimensional Euclidean lattice with periodic boundary conditions. It has sites labeled by integers. So tau hat and x hat are integers running over the sides of the lattice in the time direction. This is Euclidean time direction. Tau will always be Euclidean time. And we have Lx sites in the space directions. And we place phases e to the I phi at the sides of the lattice. And we write a Euclidean action. It should be such that phi is circle value. And as circle value, the action should be written in terms of phi, but it's invariant under shifting any of the phi's by 2 pi. So we write this action, sum over the links, the difference of phi at the 2 links, and we take the cosine. We exponentiate, we calculate e to the minus s, and we integrate over all the phi's. So it's a finite number of phi's, L tau times nx phi's. Every one of them is integrated between 0 and 2 pi. The action is bounded, so everything is nice and convergent, so this is completely reduced. This system has a global U1 symmetry connected to the question I was asked. I can take all the phi's in the system for any x hat and any tau hat and shift them by the same constant alpha. Alpha is independent of x hat and tau hat, and clearly this is a symmetry of the action because only derivatives, only differences in phi between two sides is important.
So now the notation question. Is the mu a link that's indexed?
Is what?
There's a delta nu. What's the nu enumerate?
U?
Yeah. You have
either tau hat or x hat is a coordinate.
Okay.
So mu will always be space-time coordinate and I will always be space coordinate. Okay, so this is this action and it was studied, it was really, I think there are at least 10 or 50,000 papers on this system. This is was really beaten to death. And what I'll do here will give only a tiny fraction of what's known about it. So we'd like to take a continuum. What do we mean by that? We'd like to take the number of sites to infinity, both Lx and L tau to infinity, and the lattice spacing to 0, holding physical distances fixed. And let me also assume that beta is large. If beta is large, we'd like to make all these cosines near 1, which means that all delta mu phi, the difference in phi between two neighboring sites, should be small. And if it's small, we can approximate it by a smooth function. So for large beta, every configuration where phi is not relatively smooth is suppressed by the action. There are no discontinuities in phi, and the lattice derivative becomes an ordinary derivative. Furthermore, we can expand the cosine and only the quadratic term enters. There is a half because this is what appears in the expansion of the cosine, and I dropped an overall additive constant, which is not important. So this is the action we are going to study in the continuum in the coming slides. And the relation between this action and this action is that they really describe the same physics, provided beta is large enough. But for small beta, they do not describe exactly the same physics. And for small beta, the physics of this lattice system with this action is not the same as the physics of this action. And if people have high energy background, I will just say that what I denote by beta is the standard condensed matter terminology. High energy physicists like to discuss it in terms of R, which is square root of pi beta, because some formulas look better in terms of R. Also, if you think of this as being a metric in field space, then R is the radius of the scalar field phi. But I'll let phi be 2 pi periodic. So let's understand this action and the physics of this action. First of all, terminology. This comes in the various names. The most common one is the C equals 1 compact boson. Boson because phi is a boson. Compact because phi is identified with phi plus 2 pi. It is circle valued. And C equals 1 because of the properties of the stress tensor that I'm not going to talk about. This action is free, which means quadratic, or equivalently, the equation of motion, or the Lagrangian equation of motion, or Euler-Lagrange equation of this phi is a linear equation, and that's why it's easy to analyze. So there's really no excuse not to understand this action completely. And as was suggested earlier, the Nazi who asked the question, but this was a good question about the symmetries, would like to understand the symmetries of the problem. So this problem has two symmetries. Both of them are U1. And by general principles, when there is a U1 symmetry, Amy Netter told us that there should be a conserved current. So I'm not paying attention with upper indices and lower indices, and repeated indices are contracted. I don't pay attention because I'm working with flat Euclidean space, so it doesn't matter. So we have a conserved current, and therefore we have a conserved charge. We take the time component of the current and we integrate it over space, and the time derivative of this is 0, because I bring the time derivative in. I use this equation to write it as a space derivative of something, and then I integrate by parts to find that it is 0. So the time derivative of the charge is 0. And what are the symmetries? First, we can take phi, which is now a function of continuum variables, x and tau, not the lattice variables x hat and tau hat, and I can shift it by a constant. As I shift it by a constant, here we have only the derivatives, so the action doesn't change, so this is a global symmetry. And we can follow the Netter procedure, and it tells us that this is the current, and this current is conserved, i.e. satisfies this equation of motion, satisfies this conservation equation because of the equation of motion of phi. This symmetry is the same symmetry we had originally on the lattice. But the continuum theory also has another symmetry, which is not present on the lattice. I should say that in condensed matter literature, this symmetry is called the charge of the system. In high energy physics, it's called the momentum symmetry, mostly because of the string application of this, string theory applications of this system. So I'll use the high energy terminology. I'll refer to this system as momentum symmetry. There is another symmetry which is not present on the lattice, which is known in high energy physics as winding symmetry, and in condensed matter physics, it's known as vorticity. This is not present on the lattice, and the conserved current is this. So first of all, let's check that it's conserved. If we hit it with d mu, epsilon mu is anti-symmetric in the two indices mu and nu, phi is smooth, so it's a conserved current. What it measures, the charge, measures how many times phi, which is circle value, winds around space. So if space is a circle, the field phi can wind around space, and as such, this is a conserved charge. Notice that on the lattice, this doesn't mean anything, because I can always take one of the phi's at one of the sites and move it with finite cost of action, and by doing that, I will change the number of times phi winds. In fact, it's not even well defined how many times phi winds, because phi is well defined only at a finite number of sites. In the continuum, this makes sense because phi is continuous. Before I continue, am I aiming too low or too high? It's easy for me to adjust.
I saw some thumbs up, so I think it's good. Yeah, many thumbs up, so it's good.
So I should go faster?
No. There are people say it's very good, so you just stay whatever you have now.
Okay, so how do we analyze this system? We go to Lorenz's signature. Lorenz's signature time will be denoted by T, not tau. We have the finite circumference of space is L, and we write a decomposition of phi. So phi is a circle valued function. Now from space, which is a circle, to the circle of phi, and this map depends on time. So first of all, there's a zero mode or a constant mode, which can depend on time. Since phi is circle valued, it doesn't have to be periodic, it only has to be periodic mode 2 pi, so there can be a term like that I will discuss soon, where W is an integer. W for winding, it's how many times phi winds around. And for the rest, I will just write a Fourier decomposition, which is periodic because if I shift x by L, k is an integer, so this is a good periodic function. And there's some reality condition. So far I haven't done anything. This is classical physics. I can take this phi and substitute it in the action, and then I see that all these modes completely decouple. In undergraduate physics, this is called the normal mode expansion of this system. So let's first discuss these guys. These guys, if you just substitute them in the action, they appear as oscillators. They are harmonic oscillators, and they are associated with plane waves. Plane waves of phi, where phi has momentum in space, k over L. This is the coefficient of x. In their energy, since these are harmonic oscillators, the energy is k is 1 over L. The momentum in space is k over L. The energy is the 1 over L, and then there are some coefficients multiplying this. A little bit more interesting is this guy, the zero mode. The zero mode is charged under the momentum symmetry. Recall that the symmetry shifts phi by a constant independent of x, and therefore it doesn't act on this, but shifts phi 0 by a constant. And there's a momentum conjugate to the coordinate phi 0. It's an integer because phi 0 is circle value. And the energy obtained from the Lagrangian is, if we just substitute this decomposition into the original Lagrangian, this is the Lagrangian. There's a beta because there was a beta before. There's an L coming from integrating the zero mode over x. And we go to the Hamiltonian. When we go to the Hamiltonian, the coefficient here is inverted, so we get 1 over beta L. And P0 is an integer, the momentum conjugate to the circle phi 0. So the energy associated with these modes is 1 over beta L. Notice that this is 1 over L, but there's no beta. This is 1 over L, but there's a beta in the denominator. What about these modes? If we substitute this decomposition in the action, this term leads to energy that depends on W. If the energy depends on W, so first of all, W cannot depend on time. It's conserved because it's an integer, and as an integer, it cannot change as a function of time. And the energy is obtained by just substituting in the action. It's beta because there's an overall beta out front and 1 over L. So what we see, there are 3 kinds of states in the spectrum. The plane waves of order 1 over L, the momentum states, which have energy of order 1 over beta L, and momentum and winding states, which have energy of order beta over L. So if we are interested in the system at large A, so for finite L, the spectrum is nice and gapped. But as we take L to infinity, all these states go down, and hence we say that the system is gapless. The spectrum of the Hamiltonian becomes continuous. Also, the energies of all these states scale as 1 over L, and therefore they are equally important. Now, a lot is known about this system. In fact, everything you want to calculate about this system is calculated. You can put it in Euclidean space on any Riemann surface. You can analyze the various boundary conditions. And one of its properties is it has a very peculiar self-duality known in the high energy physics as T-duality. And it exchanges beta in 1 over beta. That's not obvious from what I said so far. It's a highly non-obvious thing. And in fact, it's quite surprising because it exchanges the momentum symmetry and the winding symmetry. And the momentum symmetry was a symmetry that shifts the zero mode of phi. And the winding symmetry was there as the term linear in x. But this is a symmetry which wasn't even present on the lattice. So on the lattice, we didn't have this symmetry. On the lattice, we did have this symmetry, but in the continuum, we have 2 symmetries in a duality that swaps them, that exchanges beta and 1 over beta. Now, actually, the continuum theory that I just described exists for all beta. But the original lattice model that we started with, the one with the cosine, is what is known as a BKT transition, Kosterlitz-Tallis transition, at a certain value of beta, and its gap for smaller betas. So this continuum description that I gave here is correct as far as being the long distance behavior of the lattice system for beta large enough, but it's not correct for small enough beta. At some point there's a transition and physics changes. This was a recent Nobel Prize just for understanding this transition. And I'm not going to discuss here in detail why this is the case. If I'm asked about it, I'll be happy to do So,
Nadia, can I ask a question here?
yes, please.
So I assume this is a conformal field theory. So
Yes,
how do you see the Virasoro, high generators Ln on the lattice?
excellent question. So this system, let me go back to the action. This continuum system is a conformal field theory. It's one of the canonical examples of a conformal field theory. We can work out the stress tensor. The stress tensor is, if we go to complex coordinates out of x and tau, d by dz and d by dz bar, the zz component of the stress tensor is dt phi quantity square, and the other one is dz bar phi quantity square. And this stress tensor satisfies Virasoro algebra, and with the central extension, and c equals 1 is the value of the central extension. So this is the simplest system that has a central, that has Virasoro algebra with a central extension. Also, the current that I discussed here, this current of the momentum or winding symmetry, these two currents become Kac-Moody currents that combine with the stress tensor to a larger kernel algebra. And furthermore, if beta has special values, this is actually a rational conformal field. So as I said, this system has tens of thousands of papers written on it. It's understood from many different perspectives, and this is one of them.
Thanks.
But I emphasize that none of these marvelous mathematical features, scaling invariance, conformal invariance, Kac-Moody symmetry, winding symmetry, self-duality, etc., none of that exists on the lattice. All these things exist in the continuum, but not on the lattice. So the lattice system is what appears at short distances, and at long distances, we have another system that has more properties associated with the continuity that we have at long distances. Did this answer your question?
Yes. Thanks.
If you want, I can give 10 more lectures only about this system.
I'd like to hear that 10 lectures sometime.
Yeah, but that's not the direction I'm heading.
Thanks.
So just to summarize where we are, we started with this action with cosines on the lattice. I recall that everything is well defined. And I use this color because this is the UV. If I actually used UV, you couldn't have seen it. So I found this purple violet color. And there's a renormalization group flow or going to long distances. In the long distances, we have something in the infrared. Again, I use red instead of infrared. And at long distances, we describe it by a continuum field. When the radius of beta is large enough, we start at short distances by using this action. And at long distances, we have this continuum theory. But if beta is small enough, if this r is smaller than the kt radius, Poster-Ritz-Starlitz radius, which in my units is √2, then the system no longer flows to the conformal field theory, but instead it goes to a gap system. So this system is gapped for small beta and is described by this C equals 1 conformal field theory, described by this compact boson theory for large beta, but the continuum theory exists for all values of beta. And in fact, it has a symmetry exchanging large beta with small beta, with the system here is self-dual. So the duality exchanges something on this side with something on this side. I'd like to make one more comment on this continuum theory and the fact that it has a Metcalfe phenomenon. This will be important for us later. So this system has two global symmetries. One of them was the momentum symmetry, and the other is the winding symmetry. And I'm on the continuum because on the lattice I don't have these two symmetries. So we have the currents for two symmetries, and there is a general recipe how to couple a current to a gauge field. Now, the gauge field I use here is not a dynamical gauge field. I'm not going to integrate it over the functional integral. We just specified classical background field. So let's start with the momentum symmetry. The current was, and I make it coupled to background field by writing this. More explicitly, the global symmetry had shift phi by a constant alpha. And now I say let alpha depend on x and tau, two coordinates of the Euclidean system. Then d mu phi is not invariant under such a shift. But if I add a gauge field, which is shifted by d mu alpha, then this term is gauge invariant. So this term is nice and gauge invariant. What about the winding symmetry? We should follow again the Netter procedure. Netter tells us that there is a current. We call it was epsilon mu nu d mu phi. And now we try to couple it to a background field. So we try to couple it to a background gauge field, which I'll denote by A tilde. So A tilde is here, and this is the gauge symmetry of A tilde. If I perform this gauge transformation here, if I perform it on this term, I can integrate by parts, and I see that this is actually gauge invariant. So by doing that, I wrote an action such that the first term is invariant under the alpha gauge symmetry, and the second term is invariant under the alpha tilde gauge symmetry. However, the second term is not invariant under the alpha gauge symmetry. If I integrate by parts, I see that the action is not invariant. It is shifted by an integral of the field strength of the curvature of this gauge field A tilde. This is a very general and very typical result. We have global symmetries. We try to couple the system to background fields. I don't gauge in the sense that A and A tilde are not dynamical fields. These are prescribed background fields. It's like just the metric of the system. The system could be in different metric, but I do not integrate over the metrics. Integrating over the metrics means we're doing quantum gravity. That's not what I'm doing. I just put the system in a different background. And even though the system had both the momentum and the winding symmetry, when I couple them to background fields for these background gauge fields for these two symmetries, I do not have full gauge invariance. This is a very deep result. It's a very deep result which has many, many implications, both in high energy physics and in condensed matter physics. You will hear later in the course or in this school on SPT phases. SPT phases, this is a very achronological order of events, but SPT phases are manifestation of such anomalies. And there are many other manifestations. So going back, there is no problem with leading ordering A and A tilde. The problem is only when we turn on non-zero A tilde and we perform a transformation of alpha. Leading order, there is no problem, right? This is quadratic, one power from alpha and one power from A tilde. So hence, there is no problem with the global symmetry. The global symmetry is still there as it was before. We can use it to derive word identities. We talked about the Kac-Moody symmetry and so forth. But the system is fully consistent, and the global symmetry is still there, but the anomaly is also there. For the people who have background in conformal field theory, I would say that this anomaly is the same as the central extension in the Kac-Moody algebra of these two U1 Kac-Moody currents. So the fact that there's a non-zero in standard normalization, there's k equals 1 in this conformal field theory. There's a Kac-Moody current with central extension k equals 1, and this k equals 1 is the coefficient that sits out here. The fact that there's 1 over 2 pi, more generally, there could have been a k here. In our system, k is 2, 1.
So
But for non-zero gauge fields, we cannot preserve both the momentum and the winding gauge symmetries. This is what I said here. And I could emphasize, somebody could say, well, maybe we didn't couple them correctly here. Maybe we could fix this problem by adding some terms here. And the answer is that you cannot. You can prove that there is no term you can add that fixes this problem. You can move the problem around, say the problem is not with alpha, but with alpha tilde. You can move the problem around, but you cannot solve it. You can solve this problem. It's not a problem, it's a property of the system. You can avoid this thing not by adding a 1 plus 1 dimensional term, but adding a 2 plus 1 dimensional term. Specifically, here you could add a Chern-Simons term in 2 plus 1 dimensions, add a bulk and a Chern-Simons term in 3 plus 1 dimensions, which will not be gauge invariant on the boundary, but this variation on the boundary would fix it. So this is kind of a little bit more technical, and it will not be important for the rest of the
So Nadia, can I ask a question here?
Yes.
So this curvature term, that's the curvature of space-time of the curvature of some field configuration.
I can barely hear you, I'm sorry.
Oh, sorry. I'm asking there's a curvature term, the partial x, A tau tilde. Can you hear me?
Yes, I can hear you. There are lots of terms you can add here.
No,
But
no.
whenever,
My question is that's the curvature of something. So I wonder, is
yeah,
the curvature of space-time of the
no,
curvature?
no, this is the curvature of the background gauge field A tilde.
Okay, so okay,
So this term is the gauge parameter of A multiplying the curvature of A tilde.
okay. Thanks.
So,
That's also my question.
and then, yeah. So again, I'm just giving you a glimpse of a very general story here. So let me recapitulate of where we are so far. We have a spectrum of plane waves in momentum states, which we derived in the continuum, and we can also analyze the lattice system, and for large beta, they are essentially the same. So that's the same. There's no winding symmetry on the lattice, but at weak coupling, there's an approximate winding symmetry with the same winding states as in the continuum. So for large beta, before we take the continuum limit, there is no winding symmetry at all, and the spectrum is a little bit different. But if we take the continuum limit and we are interested at low energies, then the lattice system for large enough beta is the same as the continuum theory. And at long distances, the lattice system is captured by the continuum theory, and including the new winding symmetry, which was not there on the lattice, but exists in the continuum, and all the winding states associated with it. The self-duality that I mentioned does not exist on the lattice. If you perform the lattice computation, or you look at the lattice system, it does not have that duality that exchanges beta and 1 over beta. For one thing, it relates weak and strong coupling, and we know weak coupling is large beta. At large beta, the system is gapless, and at small beta, the system is gapped. So there cannot be any symmetry between them. Now, there's no winding symmetry on the lattice, and therefore we cannot discuss this whole story of the tooth anomaly that I mentioned earlier. It's a feature or a problem or a property of a symmetry which is not there on the lattice, and therefore we cannot discuss it. So we are driven to the following question. Can we find another lattice model which has all these properties? So we started from the lattice model with the cosine. We said at long distances, it is described by a continuum theory. The continuum description is valid only at large beta, but it can be analytically continued to smaller beta, where it does not give the same answer as the cosine. And now we would like to ask, so I formulated earlier in the talks a question, given a lattice system, what is its long distance behavior? How do we capture it using a continuum field theory? So here, for large beta, I gave you the answer. The model with the cosine is described at long distances by the continuum model I wrote down. I also formulated the opposite question. Given a continuum model, how can we find a lattice model corresponding to it? A lattice model that would make this whole treatment rigorous. Well, for large beta, we know we could use the cosine model. But for small beta, the continuum model exists, and the model with the cosine does not have it as its continuum limit. So the question I would like to address now is, can we change the lattice model and find another lattice model such that we get the same continuum model for all values of beta, such that the winding symmetry is present already on the lattice, such that this tooth anomaly exists already on the lattice. And honestly, I was taught that this cannot possibly be done because all these properties of the continuum theory depend on this winding symmetry. And the fact that there is a winding symmetry relies on the fact that phi is a continuous field in the continuum. The winding symmetry tells us how many times phi is a map from space-time, say a circle in space-time, to the target space, which is a circle. So it's a map from S1 to S1. It has some winding number. But this is very much tied to the continuum because on the lattice, phi is defined only at some finite number of sites, and we cannot discuss how many times it winds around. So I personally thought that this can never be done, but now I'm going to show how this can be done. And I'd like to pose for questions.
Okay, there is one. So just a second.
I should say that I'm going far slower than I planned, But I think that there's nothing wrong with that because this is not a course which is the prerequisite for a more advanced course. So I would rather cover less material and make sure that everybody is on board. So please ask questions.
Yeah, so this is I guess a bit of a naive question, but if we interpret beta as the temperature, then what does it mean that the XY model is gapped? That's for some beta and gapless for other beta. So what's the how do you square that with the spectrum being
the definition? I worked out the spectrum of the system in a Hamiltonian formalism. There's a spectrum of the Hamiltonian. And then I asked what happens. There's a spectrum with finite volume. The spectrum is discrete, so that's nice. And then I make the physical size, what I denoted by little l, and make it larger. And then I asked, is the gap in the spectrum of the Hamiltonian, does it go to zero as I send L to infinity, or is it held finite? If it's held finite, the gap in the Hamiltonian, as I make L infinite, I said that the system is gapped. If the whole spectrum collapsed down to zero, I said that the system is gapless.
I see. I guess my question was that there seems to be a problem with interpreting beta as a temperature because the spectrum of the system doesn't depend on the temperature.
Yeah, so okay, that's an excellent question. I tried to cheat and avoid this question, but since you caught me, I'll answer it. When we discuss these lattice models, let me go back to the introduction. Okay. When we write this thing, we can think of it in two different complementary ways. The mathematics is exactly the same, but the physical interpretation is completely different. What I said here, I took the root that this is a Euclidean action for a system in 1+1 dimensions. This was the story I told here. We have a system in one spatial dimension. There's one time dimension. I took time to be Euclidean, put everything on the lattice, and then the functional integral, which is e to the minus s, is obtained like that. And the use of the character beta here looks completely random. There's a totally different interpretation of this formula, where we say, no, space-time is not two-dimensional, but space is two-dimensional. And we have a system, a classical system, and we're doing thermodynamics. Beta is 1 over the temperature, and then this S is the Hamiltonian of a two-spatial dimensional system, and this is the Hamiltonian of that system. So the mathematics is the same. Either way, we compute trace e to the minus beta h in the second interpretation, or we compute a functional integral over phi of e to the minus the action. So the mathematics is exactly the same. This is really a remarkable thing that we have two totally different physical interpretations of the same mathematical statement. So I took in these talks, I took the point of view about this problem that I'm discussing, the Euclidean description of a 1+1 dimensional quantum system at 0 temperature. This turns out to be the same as a classical system, not quantum, but classical. There's a Hamiltonian, this is the Hamiltonian, and we compute e to the minus beta h in two spatial dimensions. So these are two complementary interpretations which are completely different. They apply in totally different physical systems, but the mathematics of them is exactly the same. Did this answer your question?
Yeah, great, thank you.
Yes.
No other questions. Please continue then.
I'm sorry?
Oh, no other questions.
No other questions.
Yeah.
Okay, so I'm going to change the problem. So let me recall where we were. We had this lattice model and the continuum model. They are the same at large beta, but they're not the same at small beta. And in any event, the continuum model only captures what the lattice model does at long distances. And now I would like to present another lattice model, which is very similar to the original one. And this was done by Mr. Rillen, believe it or not, before I went to school. So this is really ancient. And Mr. Villain said, we had this phi, which was circle value. Let's pretend that phi, we're going back to the lattice. We have a two-dimensional Euclidean lattice. And we had phi, which was circle valued. We had a circle valued integration variable in the degree of freedom at every side. And let's make believe it's real. And if it's real, we're going to couple it to an integer valued gauge field on the links. And I'm going to write the following action. So what's going on here? I write this action. Delta mu is the lattice derivative, or the difference across the link. And mu is an integer that lives on the link. And this action is invariant under shifting phi by 2 pi times k and shifting n mu by the lattice derivative of k. More mathematically, the variables n mu form a gauge, are the connections of a Z gauge theory on the lattice. So what is a Z gauge theory? It means that on every link of the lattice, there is a connection A, connection nu, which is an integer. It tells us the holonomial as we go across the lattice, or across the link. And we write this action, which is gauge invariant. Now, since we have, and this K is a gauge symmetry, it's an integer that depends on the size. Now, we can pick a gauge such that all the phi's are between 0 and 2 pi. So they started their lives as being real numbers, but I can pick a gauge that all the phi's are between 0 and 2 pi. And then I have some sum over integers to perform. Or in the functional integral, I have to integrate over phi, and I have to sum over the ends. I could also choose other convenient gauges. Now, this action is very close to the story with the cosine. We have these degrees of freedom phi, which are circle valued. In the theory with the cosines, they started their life as circle valued variables, and they remain circle valued. Now we say, well, they're really real numbers. Each phi is real valued, but there is a gauge symmetry that makes it effectively circle valued. Now, unlike the action with the cosine, this action is quadratic. It's quadratic in phi and in nu. And therefore, it's easier to analyze. And its physics is very similar to the original physics of the original nonlinear action with cosines. And we can repeat the whole discussion we talked then, and everything will be true. There's a momentum symmetry, there are plane waves, we can discuss what happens in the continuum limit, and everything I said before follows just the same. But now we're going to modify this action. So we can ask, are there any other interesting terms that we can add to this action? And our guiding principle is this gauge symmetry here. So if we have a gauge symmetry, we have a curvature. And this is the curvature square of this integer value gauge field. And we can add this term on every plaquette. So the ends are on the links. The curvature is on the plaquettes. And we can add it with coefficient kappa. So we can add this term to the action. So the action now depends on the value beta and also on another parameter, kappa. And we are going to be interested in the limit kappa going to infinity. As kappa goes to infinity, all the terms where the curvature of this gauge theory is non-zero are going to be suppressed. Because as kappa goes to infinity, the only configurations of n that have non-zero action, non-zero contribution, to e to the minus s, are those where the curvature vanishes. So what we say is we write the action in the Villain form, and now we say that the gauge field of the Villain formulation, this nu, is constrained to be flat. So this is what we do. It's not the original system, it's a deformation of the original system with a parameter kappa. And now if this is, we want to constrain the curvature to be 0, and the easiest way to constrain the curvature to be 0 is to add a Lagrange multiplier. So we refer to it as the modified Villain action. So this term we just copy, and instead of having this term with kappa going to infinity, instead I'm adding a Lagrange multiplier field phi tilde, and recall what we're interested in is e to the minus the action. So when we integrate over phi tilde, it constrains this thing to be 0. So So instead of sending kappa to infinity, I add this Lagrange multiplier, and it constrains this to be 0. So this is the action we're going to study. Notice that in this action we have an I here. It exists in Euclidean space. It does not exist in Lorentz signature. So this is very Euclidean physics. And the interpretation I mentioned earlier in terms of temperature does not work very well, because when we have the interpretation for thermodynamics with beta being one over temperature, we cannot put such terms with an I in the Hamiltonian. But for our Euclidean interpretation, this is completely valid. This, I should say, does exist also for the Euclidean, also for the thermodynamic interpretation. But this trick of writing it with the Lagrange multiplier does not. So this action turns out to be very similar to the continuum action we described earlier. So first of all, it's free. So we started with phi, no cosine, no nonlinearity from phi, which is quadratic in phi and n, and also n tilde. It's free. And it has two global symmetries. First, we can shift phi by a constant. That's clearly a symmetry. This doesn't change because it depends only on delta mu phi. And this doesn't change because it doesn't depend on phi. And there is a net product. But we can also shift phi tilde by an arbitrary constant. So if we shift it by a constant independent of tau and x, then this is a total derivative. And therefore the Lagrangian, or the Lagrangian density, is not invariant, but the action is invariant under this shift. And indeed, there is a net current. So this will end up being the winding symmetry, and this is the momentum symmetry of the continuum theory, but now we see it already on the lattice. And we can follow the manipulations I did for deriving the 't Hooft anomaly. We can try and say, let's couple these to gauge fields on the lattice. I'm not going to do it here because it's essentially as the manipulations I did in the continuum. And you can find that this system is essentially as in the continuum, and there is an 't Hooft anomaly already on the lattice. So you might have heard somewhere that the 't Hooft anomaly is a very mysterious thing, depends on the fact that we need to regularize the continuum theory, or it cannot really exist on the lattice because there's a whole business of system that acts on site or not on site. Here, the action in the Lagrangian formulation, the action of both symmetries is on site. And the subtlety is that the Lagrangian density is not invariant under this shift, but the action is invariant under these shifts. And therefore, we can have this 't Hooft anomaly. I'm not going to do it here in detail, and I'm also running out of time. So I would just say that on general grounds, the fact that this system has an anomaly tells us that it must be gapless for all time, for all beta. So this system is always gapless. Second, we can perform, you see, if you look at the action, on every link, we have an integer, n mu. Here it's written as nx and n tau. And the action is quadratic in n. So there's a standard trick in mathematics. It's called Poisson resummation, invented by, this will be a question for the exam, who invented the Poisson resummation? And we can perform Poisson resummation on this action. And if we perform this Poisson resummation, find phi tilde are exchanged, and beta is inverted. So this T-duality, this surprising T-duality that we had in the continuum, now exists already on the lattice. And this is a nice exercise that does not need any of the knowledge of the physics that I described here. Just look at e to the minus this action and use Poisson resummation, which you can read about in Wikipedia, and see how fine phi tilde switch roles, and beta is inverted. So for small a and large L with fixed little l, we find the same spectrum and the same momentum and winding symmetries, and everything we talked about, the continuum theory, remains true. So this lattice model is very close to the continuum theory, and it provides a good regularization of it. So this lattice model is completely finite number of sites. Integration region is such that the action is bounded. all the integrals converge, all the sums converge, everything is meaningful, and that gives us a nice regularization of the continuum theory, much better than the action with the cosine because it exists for all beta. So let me summarize it as follows. This is the action we started with. For kappa equals 0, we have this Milan action, which is very similar to the action with the cosines. And before it was in this purple, this is kappa equals 0. And at long distances, there's a renormalization group flow. It goes to the red line for beta large enough. And then it goes elsewhere, becomes gap for small values of beta. This other action, and actually the same is true for every value of kappa, which is not infinite. But in the limit kappa goes to infinity, we have this brown line, this action, and this action is such that it flows to the continuum model for all values of beta. So you see this flows the same, this flows the same, and while here this action flows to a gap system, this one continues to flow to the gapless C equals 1 system. So my time is up. I'll be happy to answer questions. I am far, far behind my schedule, but I think that's fine. What I will do next time is to. So this is a system that we fully understand. This system was analyzed in a lot of detail in the 70s. It has experimental realizations. It's really fully understood. But next time, I'll use the same language to describe a system which is much more subtle, which is an exotic system with subsystem symmetry. And we'll see how the discussion changes when we have a subsystem symmetry. So are there any questions?
Okay, any questions? Okay, here we go.
So if so you mentioned that in the continuum theory you have the U1W, which is the winding symmetry, that is an emergent symmetry, right?
Yeah.
When exactly does that come about when you go from the lattice to the continuum? Like what changes?
Okay, so on the lattice it doesn't exist. There's no such symmetry on the lattice. The easiest way to see that is that if you look at space and you have this circle value variable at every side of the lattice, if phi changes slowly, you could say, oh, I can define something like winding. So phi star, I don't know if you see my hands. Phi changes slowly, and you can count how many times.
We actually don't.
Sorry?
We don't. We don't see your hands.
Oh, you cannot see my hands. Can you see my hands now? Okay, so on the lattice, we have phi's at every point, and it's circle value. So I can approximately say, oh, I can keep track of how many times it rotates as I go around. But this is meaningful only when phi changes very, very slowly from side to side. Because if phi start changing rapidly, I cannot even define how many times it winds around. Another way of saying it is that imagine phi is already in the continuum. Phi is almost constant, and then it very rapidly winds around, and then it continues to go almost constant. So it can wind over a very small region. Now, if we have a lattice, this region can be localized in space in between two lattice sites. So on the lattice, there is no notion of winding. However, what we have here is an action with this beta cosine that suppresses phi, which is very different at nearby sites, because we have beta times the cosine of delta phi. So we compute delta phi between two sites, we compute the cosine. So if delta phi is not very small, we are penalized by it in the action. And in the functional integral, these configurations are suppressed. So what we end up with are configurations where phi changes very, very slowly. And if phi changes very slowly, I can define the winding. This is a general thing that when we have mapped from one manifold to another manifold, we assume that the map is continuous. And when the map is continuous, I can define the winding number of the map. But if the map is not continuous, I cannot define the winding number. But if I say that all the configurations which are not continuous are really suppressed, then I'm only talking about the configurations that are continuous, and then I can define. So what really happens more physically is that we have a winding symmetry, but it's slightly variable. And as long as we're talking about processes at very low energy and at very low distances, we do not see the violation of the symmetry. So the continuum theory this is known more technically in condensed matter physics, it's known as an emergent symmetry. In high energy physics, this is called an accidental symmetry. A symmetry which is not present at short distances, but it does exist at long distances. And then the question arises, is this symmetry robust? So once we have such an emergent symmetry, imagine we change the system a little bit at short distances. We change the system a little bit at short distances. Does it ruin this property we found at long distances or not? And this is something that has to be analyzed on a case-by-case basis. So in the example with the cosine, the momentum symmetry was already on the lattice. The winding symmetry was not. By the time we went to the continuum, both the momentum and the winding symmetries were there at long distances. And they played a crucial role in the analysis of the system. This whole discussion of Kac-Moody symmetry and central extension, this whole thing cannot even be studied. We cannot even study it if we don't have the winding symmetry. So this winding symmetry is really central. But it's not present on the lattice. It's only approximate at long distances. The other lattice model that I presented is quite marvelous because it has both the momentum and the winding symmetry already on the lattice. So somebody could have said, Zheng Han could say, yeah, it exists on the lattice, that I understand, but the continuum is slippery. We call that quote. The continuum is slippery. And since it's slippery, do we really know that the winding symmetry is there? Do we really know that all the consequences of the winding symmetry are really there? Because I really needed the continuum for that. I needed the continuous map from phi, which is circle value, to space, which is circle value. But on the lattice, there's no notion of continuity. So can we really trust it? Now, for decades, physicists have been analyzing it, and there's a lot of confidence that this is right. But Zheng Han tells me it's slippery. So my response to that, yeah, you're completely right. It's slippery. But this action, this modified Gulen action, has the symmetry already on the lattice. So this action, let's see if I can get it back in here. This action, share the screen again. This action has the momentum symmetry and the winding symmetry. Oops. Oops, I can't do that. Okay, so this action has both the momentum symmetry and the winding symmetry. It exists already on the lattice. And the argument that the continuum is slippery says, yes, it's slippery, but it actually got the right answer because here I found a regularization of the continuum theory that has both the momentum and the winding symmetry. And all their properties, the T-duality, this self-duality of these two that exchanges phi tilde and momentum and winding and inverting beta, and the Tooth anomaly between them, all these properties exist already on the lattice. So this is very reassuring because it tells us that all the manipulations we did on the continuum, and nobody doubted they were right, but all these manipulations can be done on the lattice, and on the lattice, everything is manifestly kosher. Everything is manifestly correct because everything is nice and finite.
Thank you so much.
But so Nadia, I do have a quick question about your action. So since you changed kappa from a real number to imaginary I, does unitarity will constrain your configuration of the fields? Hello?
Yeah, so I didn't change kappa from real to imaginary.
Yeah, I wonder if
What
unitarity
did they
would.
do? Let me go through this steps. Chi was real, so everything is nice and unitary. More precisely, reflection positive. So
Okay.
kappa is real. So at this point, you don't complain,
Yeah,
right?
yeah, I
So
don't.
far, so good.
Yeah, so far so good.
So now I'm going to at this stage, kappa is still real.
I'm happy here.
Sorry?
I'm happy here too.
So here kappa is real, everything is nice. I'm
Yeah.
taking it to infinity. What
Yeah.
it does, it constrains this thing here. Can you see my cursor?
No, we cannot. I can see the cursor, but it's not moving.
Now it's moving.
Okay.
Can you see it now?
Yeah.
So it constrains this thing to be 0. So this is still nice and reflection positive.
Mm-hmm.
Then you could have asked your question here.
Yes.
What is this I doing here?
Mm-hmm.
What is this I doing here?
Yes.
I did not make kappa imaginary.
Mm-hmm.
I did not make kappa imaginary. I sent kappa to infinity, and then I say kappa equals infinity is the same as integrating over phi tilde. So now you could ask your question here. Is this reflection positive?
Yes, that's the
And
question.
the answer is yes, provided that under the action of reflection positivity, phi tilde flips its side.
Okay, okay. That's answer my question.
This is completely unitary. It's as unitary as this.
Okay. Okay, that's my question. If no other questions, so let's thank Nadia again for great talk.